So this is about the theory of machines class, which is about two things. One is mechanisms. The second is vibrations. Most of it will be about the mechanisms, their analysis. But then there will be a part in which there is some vibrations. So the course content is as follows. We have introduction to mechanisms, which we will partially do today. And then there will be some basic concepts like mobility, which is the same thing as degree of freedom, and some basic mechanisms. Then we will analyze the kinematics of mechanisms, which means position, velocity, and accelerations of mechanisms, how they are related to each other, and how we can find out what kind of velocities and accelerations develop inside the mechanisms. Okay, then we will go to a specific kind of mechanism, which is kind of important, gear trains, in which we will look at the kinematics of gear trains. Sorry, somehow I cannot manage it. And then we will do, up to now, we will be dealing with kinematics, and then there will be static and dynamic force analysis. So the force is the key word here. Force analysis will be done, the causes of the motion. So until this point on, it will all be kinematics. Then this will be kinetics, where you analyze the forces. And then this will be the end of mechanisms. And the last month or so, last 3 weeks or 1 month, we will look at vibrations, which is an important topic by itself. But unless you take the mechanical vibrations course, this is all you are going to learn about vibrations during your education. So we are going to introduce it to you in order to have some idea about some basic concepts of vibrations. Okay, so let's continue. So our objectives in the course is to answer some very basic questions, such as what is a mechanism, what kind of a thing is mechanisms, and what are its components, what is it made up of, and what is the degree of freedom of a mechanism, what does it mean, and how do you find it out? Okay. And then we will, as I have told you, we will be doing kinematic analysis for some time, which will be an important part of the course. So you will be able to perform position, velocity, acceleration analysis of planar mechanisms and gear trains. Actually, this part you have learned in dynamics, but we are going to go through it and teach you through a new concept called, the complex number method, which is kind of easier to analyze. In the dynamics, we try to teach this kinematic analysis through vectors. Okay, here we will also use vectors, but we will use complex numbers next to vectors. Then we will be doing the force analysis of mechanisms, so that you can find out the forces in the mechanisms. And then we will introduce the vibrations, in which you will learn some basic concepts, how to model a vibrating system. What does natural frequency, for example, mean? What does resonance mean? And when does resonances occur, and how to avoid them for simple machines, let's say. It's not going to be very comprehensive, but it will be an introduction. So we will start, as I said, with a mechanism. Well, what is the difference between machine and a mechanism? Let's say that is a obvious question. because machines are the general name we give to devices that accomplish work, that do some work. I don't know, washing machine, for example, washing the clothes, or a construction machinery moves pieces from one place to another. A lathe, let's say, cuts pieces and so on. These have specific tasks. A robot, for example, moves from one place to another. Mechanism is something inside the machine which allows the machine to do that task. It is the mechanical portion of the machine that transfers motion and forces. So motion and forces are two dual couples, let's say. Whenever there is motion, there should be some forces. And whenever there are forces, there might not be motion. But anyway, so mechanism is a more smaller part of a machine, which is the mechanical part, which makes the motion possible, let's say. Okay. So we will analyze mechanism as rigid elements. So we will assume that they have infinite stiffness. They have no elasticity. And we will call these elements linkages. Okay, linkages. And they are connected to each other. The linkages will be connected to each other to perform specific tasks so that they will transmit motion and force in a predetermined fashion. I will give you examples of this. As I have said, for example, the mechanism is made up of links, the so-called links, or previously I have called them linkages. Linkages, the connection of links it's called linkage, I guess. So we assume the links to be rigid bodies. So they are basically rigid bodies, pieces of rigid bodies that are connected to each other. This is what we are going to assume for the analysis of mechanisms. They have joints like nodes on each of them for attachment. You can attach them to each other. They can be connected to each other. So they can be of any shape, although we idealize them with very simple drawings. Their shapes can be quite arbitrary according to the needs of the design. We can talk about the order of the links according to their number of joints, number of nodes, let's say. Node and joint are synonymous, they are the same thing. For example, a binary link has 2 joints, okay? A ternary link has 3 joints, so that it can be connected to 3 different, this one can be connected to, the one in the middle, can be connected to 3 different, let's say, links. And quaternary, for example, can be connected to 4 different links, etc. So this is the order of the link. This is called. I'm trying to introduce some of the terminology here, which we will be using throughout the course. Now on the top of links have to be connected to each other by something, right? Let me, how can I do this? Let me stop this sharing and let me share something else. A whiteboard so that I can draw. So the links are, things like this, okay? It's a rigid body. So we put on them some joints, okay? So that this is a link, this is a joint. So we can connect them to each other, 2 joints to each other. This is 1 joint. There is let's say, a joint here. Through the same joint, we can connect another. Something wrong again. another joint here, and this is a pin joint, so that two joints, this is one, let's say this is two, they can move relative to each other, okay? So that this is a so-called a revolute joint. Another possibility is, for example, this is one joint, sorry, it's one link. This is another link. You know, the two can slide with respect to one, let's say. Okay, so that this is called a prismatic joint. This is let me stop this and go back to our PowerPoint. So I try to introduce that by drawing. So our main joints are the revolute and the prismatic joints. The one at the top. The revolute joints connect two linkages, as you see, and there is a pin in between them, so that it allows relative rotation with respect to each other. Okay. The second important one is the prismatic joint, that's what it is called, in which the one thing translates with respect to the one link, translates with respect to the other one. So it allows relative translation. Okay, these are the most common links we are going to use, but there are, of course, other possible links. For example, I will come to these later on. For example, you might have link against plane in which you have two possible motions, or pin and slot in which again you have two possible motions with respect to each other. Okay, or you might have, for example, as you see down here, a spherical joint in which two links can move with respect to each other and make three rotations. But these are kind of more advanced. I will talk about these later. Just keep in mind that the most common joints we have is revolute and prismatic, R and P. Keep these in mind, okay? For we will be using most of the time these two, but there are others which you have to know. Okay, let's go on if we can. Now, what are the mechanisms? For example, what is a mechanism? And the most common mechanism, there are two most common mechanisms which we will encounter all the time in this course. One is the four-bar mechanism or four-bar linkage. Linkage is again synonymous with mechanism, in which you have four bars connected to each other, okay? Well, you see here, of course, there are not four bars, there are three bars, as you see, 2, 3, and 4. But the idea is that you fix one of the links. So the ground is another link, okay? There is a link between A0 and B0 here, as you see, which is the fixed link. The fixed link makes up the first link, or according to your counting scheme, it is the fourth link. So the input links makes a rotation, and the follower link makes a rotation, and in between there is the coupler link, which traces a certain path, well, a certain point in that coupler traces a certain path, and that path can be, well, by using the design, it can be something very interesting. That is, you can design the possible path by selecting the mechanisms, let's say, dimensions. Okay? So the four-bar mechanism is very important. If you encounter it everywhere, all kinds of machines have four-bar mechanisms inside them. For example, the garage door openers or the let's say sofas, the sofas that you can open and close. You know, the yatak, açılabilir yatak yani. The beds that can be opened and closed. For example, they have 4-bar mechanisms. Also, the windshield wipers inside the cars used to have 4 bars. Well, not anymore because they are digital now. And so on. 4-bar linkage is extremely common. The second common mechanism is the slider crank mechanism. There is a crank which rotates. There is a slider. This one goes back and forth. And there is a coupler which connects the crank and the piston or the slider. Now, this is a very common mechanism as well. As you probably know, this is the mechanism that is used in internal combustion engines. That is the car engines, that is. It is used to convert translational motion of the piston to rotational motion of the crank, so that that crankshaft, it is transferred to the crankshaft, and crankshaft drives the car. So that is probably the most common application, but there are other applications of this slider crank mechanism. Main function is to convert rotary motion to translational motion and vice versa. It converts rotary motion of crank to translational motion of the piston, which is back and forth, or what is it called? Transmits or it just changes let's say, the piston motion to rotational motion of the crank. Okay, this is a very common mechanism, and we will be analyzing this one in detail as well. So these two mechanisms you have to keep in mind for now. These are the most common, 4-bar and the slider crank mechanisms. Okay. We have to make here a distinction between analysis and synthesis. In this course, we will be dealing with analysis only. Synthesis is a more difficult task. What we are going to do is, if you are given a certain mechanism with all its dimensions and so on, and its velocity, well, input velocity specified, you can and you should analyze the positions, velocities, and accelerations at all points, at all possible points. So you can perform kinematics and kinetic analysis. Analysis, as I said, is the easier task. Synthesis is more like design. So you design a mechanism to perform a specific function. For example, you want to design a mechanism to generate straight line motion, let's say, by a 4-bar mechanism. Well, there are certain techniques to do that, of course, but synthesis is the more difficult task, and we are not going to be dealing with synthesis in this course, okay? How do we do it? Both analysis and synthesis can be done by graphical techniques, which is kind of old now because we have computers nowadays. Graphical techniques usually rely on drawing, but still you can use graphical techniques to get some idea about what you are doing. And more commonly nowadays, we will be using analytical methods. The analytical approach is the more common and well, better maybe approach, but you have to have an understanding of graphical techniques as well. Okay, let's continue. This is just another definition. Mechanisms, kinematic, this is another notation. Mechanism is just obtained by, let's say, connecting rigid bodies by joints, okay? But I wanted to tell you this notation. The kinematic element is used for the links or the rigid bodies, and the kinematic pair is used for the joints, okay? This is a notation which is sometimes used in books. For example, in Eres Hoca's book, we have sometimes this notation. So I wanted to make you aware of this. Okay, the kinematic pairs can be open or closed, but this is, let's skip that. And let's go to degree of freedom for the time being, because this is an important concept, which we will be using starting from next week. So we will try to understand the degree of freedom of a mechanism. But degree of freedom of mechanism is confusing because there are more than one degrees of, well, more than one definition of degrees of freedom. You can have degree of freedom of a space, degree of freedom of an element or a link, degree of freedom of a joint, and the degree of freedom of a mechanism. These are all different things. So let's start from, they are all related, but they are different. So let's start from the degree of freedom of a space. Let's say that we are in two-dimensional space. Let's say we are in the plane, like the plane of your computer or the plane of the table, so that your mechanism is two-dimensional. It's not three-dimensional. In this course, by the way, we will be analyzing only two-dimensional mechanisms. I will briefly sometimes talk about three-dimensional mechanisms, but not much. So our main concern will be plane mechanisms. So we will be interested in two-dimensional mechanisms. So the degree of freedom of the plane is important for us. What is the degree of freedom of a plane? What is the degree of freedom in a space, actually? In a two-dimensional space, how many motions are possible for a rigid body in two dimensions? Let me just stop this and let's try to share our whiteboard so that let's erase this. Okay. No. I don't want a vanishing pen, I just want a regular pen. Okay. Sometimes things go wrong with this. Okay, so we have a two-dimensional space like X and Y. And we have a rigid body here in this plane, let's say. This rigid body has how many motions does it have? Well, it is an ambiguous question, of course. It can move in this x direction, right? It's a possible motion. It can move in the y direction. But is this all? So the two motions are possible, x motion and y motion. You can, have another motion which can be combination of x and y motions, but these are the main things, let's say. But then what else? Is this the only motion that is possible? Well, there is one more actually, which is a possible rotation, okay? So a rigid body in 2 dimensions can make 3 motions, so that the degree of freedom of a rigid body in the, let's say, degree of freedom of a rigid body is 3. And we call this the degree of freedom of 2-dimensional space is 3. Okay, because 3 motions are possible for a rigid body in 3-dimensional space. Is this clear for everybody? Or does anybody have questions? Usually this is a concept that's not very easily understood. So for 2-dimensional space, for plane, the degree of freedom is 2. Sorry, 3, not 2. By the way, am I sharing it with you? Yes, I am sharing, right? So let's go back to our PowerPoint. Okay, chat says what? Yes, okay. So the degree of freedom of a plane is 3. There are 3 possible motions in the plane of a rigid body. How about 3-dimensional space? In the 3D space, it's more difficult. It might not be very easy to imagine, but the degree of freedom of an object that is a rigid body in 3-dimensional space, just a regular object in, like this pen that is moving. You probably cannot see it, but this pen moving in space like an aircraft or something. How many degrees of freedom does it have? It has 6 degrees of freedom, okay? 3 translations, X, Y, Z directions, but on top of that, there are 3 rotations. Again, rotations about x-axis, rotation about y-axis, rotation about z-axis. 3 translations and 3 rotations are possible. Therefore, the degree of freedom of 3-dimensional space is 6. An object in 3-dimensional space has 6 degrees of freedom. 6 motions are possible for an object in 3 dimensions. So just keep this in mind. We will be using these in the coming lectures. Okay, we talked about the degree of freedom of space, and now let's talk about the degree of freedom of a kinematic pair or a joint. Kinematic pair is the more sophisticated way of saying joint, okay? So in this case, if you have a joint, what is its degree of freedom? It is the, let me show it to you by example. Well, first of all, the joints in general reduced to 2 degrees of freedom of links, okay? How is that possible? For example, look at the top picture. You have 2 links there, and how many degrees of freedom of these 2 links have in 2-dimensional space? The first one has 3 degrees of freedom because it's in 2-dimensional space. The second one has 3 degrees of freedom as well. In total, their degree of freedom is what? 3 plus 3 is 6, right? The total degree of freedom is 6 here. But if I connect them with a pin joint here, okay, or a revolute joint, it is called an R joint, the degree of freedom now decreases. How is it? How does it decrease? Now these 2 things are, well, their motions, translational motions become the same. They don't have a delta y1 and delta y2, but rather a delta y here. Because those delta y1 and delta y2 have become the same. And so is delta x1 and delta x2. It has become delta x. And then there is a delta, this one still has delta theta 1, and this one still has delta theta 2. But now the degree of freedom has decreased, as you see. It has decreased by, well, actually 2. Instead of 6, now you have the degree of freedom of 2. Okay, sorry, degree of freedom of 4. So somehow this thing has decreased the degree of freedom. Let me go to the previous one. So this is, of course, a complicated definition, which you probably will have difficulty understanding. It says that the degree of freedom of a kinematic pair or a joint is the number of independent parameters that is required to determine the relative position of one rigid body with respect to another one. So what does it mean? It means the following. It means, for example, in order to determine the relative position of this pink joint with respect to this, let's say, what is it, this gray joint, you need only one parameter, and that will be delta theta 2. So the degree of freedom of this revolute joint is just 1, okay? So with respect to the first one, the second one can make only one possible motion. If you hold the first one constant or fixed, the second one can only make one motion, which is a rotation. So the degree of freedom of this joint is 1. Okay. For example, in this rolling and sliding joint, the degree of freedom of this joint is 2 because this pink joint can make 2 possible motions. One is delta x2 and the second is delta theta 2. So the degree of freedom of this joint is 2. So the most important joints we have is revolute and prismatic joint. Revolute joints and prismatic joints have 1 degree of freedom. Okay, their degree of freedom is 1 because the motion of one link with respect to the other one there is only one motion is possible. And in the revolute joint, it's rotation. In the prismatic joint, it is translation. Okay. Remember revolute and prismatic joints. Okay. There are higher order joints. I will come to explain these to you later on. For example, a cam joint or a gear joint have 2 degrees of freedom. Okay, 2 motions are possible with respect to each other. Don't ask me why and how now. I will explain this later next week. So there are simple links and complex links that can be formed using these mechanisms as well. Now, so much for this introduction. I tried to give you some very basic concepts here, like the degree of freedom, links, joints, how they are connected, how the degree of freedom is decreased by connecting them, and so on. We will use these next week when we talk about the degree of freedom of a mechanism. This will be the end of our first lecture. Well, this lecture, that is. From now on, I will give you some basic mechanisms. I will explain you some basic mechanisms. But I guess we can take a break here and come back and, you know, look at some common mechanisms that are used in machines. We will be looking at things like presses, window opener, and so on. These are kind of fun mechanisms that can be used in machines. We will come to look at that in the next hour. So let's stop recording.